So we're going to look at double integrals over general regions. Now, what we have here is, in the last section we integrated over rectangles, but that's not always helpful. So here we're going to look at it over general regions. You can see in this first box, it says that for single integrals, we wanted to integrate an interval, and we looked in the last section at rectangles, but what we're looking at here is a figure where it's not necessarily a rectangle, it's a more general shape. So we can have a bounded region where f of xy is in the domain, or 0 if it's in the rectangle but not in the domain. And here we put that into 3D. We can kind of see we have the graph of D and we're finding the volume under the graph of D. So the double integral equation in this third box looks exactly the same. We have a capital F of x in the second part because we're looking at capital F, this equation up here. So what we're looking at is we're looking at finding the volume under a surface, not in a rectangle, but inside of a different shape. Now what we're going to see is we're going to look at that in terms of systems of equations. So let's continue on. So we're going to look at type 1 here. And in type 1, what we're going to say is that our boundaries are functions of x. Our boundaries are functions in terms of x. This is going to feel a lot like area between the curves in Calc 2. So we're going to say that our region D, that funny shape, you know, we had that funny like kidney bean shape D. So our region D is the set of points x, y, such that x is between A and B. But instead of saying y is between C and D, we say y is between the first function of x and the second function of x. Second function in terms of x. An example could be, remember in Calc 2 when you had a parabola and you had a line intersecting it? So this is your first, this is g sub 1 of x, which equals x. And this would be g sub 2 of x, which equals x squared. So you can see how your boundaries then are going to be functions in terms of x, and y is between them. So here we have the notation. It says if f is continuous on a type 1 region, and in a type 1 region, that's when our functions are in terms of x. So we can see that x is between a and b, and y is between the two curves. Then our double integral is written as such. The integral from a to b, the integral from g1 to g2, f of xy dy dx. So you're going to put the x's you're going to put the dy in the middle because you're going to have x values in those bounds before you integrate in terms of x. And then let's look at a couple graphs of what this looks like. So here are a few type 2 graphs, and you can see that the y values fall into the D range, and then you can integrate accordingly. So before we look at the type 2 graphs, let's go ahead and do one of these problems. Now this problem says to evaluate the double integral, and D is the region bounded by those two equations. When you look at these two equations, look at the fact that they're in terms of x, so this means we have a type 1. So we have a type 1 region here, so we're going to do the double integral. And the type 1 region says that I'm going to do the double integral of x plus 2y. And my bounds are going to be dy and then dx. Because I have my two equations, and then I have my y values. Now, I don't have any of that. So in order to do that, we have to actually look at the graphs. So let's talk about y equals 2x squared and y equals 1 plus x squared. Y equals 1 plus x squared is a parabola which moves up 1 and looks like this. So this is y equals 1 plus x squared. And then y equals 2x squared is a skinnier parabola that comes through like this. We could say stretched. So y equals 2x squared. So this is what you're looking at, is this is the region between the two. So that tells me my lower boundary is 2x squared, and my upper boundary is 1 plus x squared. So that gives us our lower and our upper bounds because we're reading it like we did the area between the curves in Calc 1 and Calc 2. So now we need the points of intersection for the x values. So to find the points of intersection, we're going to set them equal to each other. There's lots of ways to do it. You could read the graph. I like algebra. So 1 plus x squared equals 2x squared. So 1 equals x squared, so x equals plus and minus 1. So our bounds for x are -1 to +1. And now this problem isn't too difficult. The setup is probably the hardest part for most of these. So we're going to integrate with respect to y. We're going to do -1 to 1. When I integrate x with respect to y, we put a y on it, and 2y becomes y squared from 2x squared to 1 plus x squared. And then we're going to say our dx is at the end. So we're going to integrate from -1 to 1, but we're going to plug in y. So I have x times 1 plus x squared minus, let's go ahead and say minus 2x squared plus 1 plus x squared squared minus 2x squared squared, all integrated next with respect to x. So we have the integral from -1 to 1. I'm going to keep my brackets. So I have x times 1 minus x squared minus 2x squared. Remember that when you square a binomial, you need to write it twice and do FOIL. So we have 1 plus 2x squared plus x to the 4th minus 4x to the 4th with respect to x is our next integration. So we have the -1 to 1 integral, and I have x minus x to the 3rd plus 1 plus 2x squared plus x to the 4th minus 4x to the 4th. Well, that's going to be nice right there. All right, so let's combine like terms before we integrate again. So we got -1 to 1, and let's start with the constant. So I have 1, and then I know I'm going to go in ascending order instead of descending order. It can go either way. I have a lonely x over here, so we're going to say plus x. I have a 2x squared. I have a minus x to the 3rd, and then I have a minus 3x to the 4th with respect to x. All right, so let's go ahead and integrate this mess. I'm going to switch colors because now we're integrating with respect to x. So we get x plus 1/2 x squared plus 2/3 x to the 3rd minus 3/4 x to the 4th minus 3/5 x to the 5th from -1 to 1. Now there's symmetry happening there, and you could play that game, but I'm going to play the -1 to 1 game. So I'm going to have 1 plus 1/2 plus 2/3 minus 3/4 minus 3/5 minus -1 plus 1/2 -2/3 -3/4 positive 3/5. I'm going to combine like terms. So I'm going to go 1. I'm just going to change the signs and bring them down to see what cancels and what doesn't. So these all come down like the same. Now I'm going to distribute the negatives. So I get plus 1 minus 1/2 plus 2/3 plus 3/4 minus 3/5. Now some of those should cancel. So the -1/2 will cancel, and the 3/4 will cancel, and it looks like that's about it. So I end up with 1 plus 1 is 2, 2/3 plus 2/3 is 4/3, and -3/5 and -3/5 makes -6/5. So common denominator here gives me, I'm going to do 15, so I have 30 plus 20 minus 18 all over 15. 30 plus 20 is 50, minus 18 is 32 over 15. So that is our area of x plus 2y bounded by the parabolas that were given. So it's an interesting problem. Let's go back to the top. Notice that you have to build your double integral correctly, and it's a type 1. So our bounds, first of all, are in terms of x when we integrate with respect to y, and then we need to find the points of intersection to find the bounds in terms of x. Now let's talk about type 2. So for type 2, our boundaries are functions in terms of y. So we're going to say that D, the general region D, as defined before, is going to be the points xy, such that for a type 2 region, y is between c and d, just like we've defined it before, and x is going to be between h1 in terms of y and at h2 in terms of y. So just like we talked about before, but instead of in terms of x, we're going to look at these in terms of functions of y. So here we have two pictures being shown, and we can see that there are definitely regions in terms of equations in terms of y. So we're going to say that the double integral then is, and notice that we have our dx first, our inside integral is dx, and the bounds are h1y to h2y, and our second integral is the integral in terms of y, and it goes from c to d. So let's look at an example of one of those. So this one says to evaluate the double integral of the region of xy, where D is the region bounded by the line y equals x minus 1, and the parabola y equals x squared, y squared equals 2x plus 6. So when you look at this parabola, y squared equals 2x plus 6, if you think of this in terms of y equals the square root of 2x plus 6, and y equals negative the square root of 2x plus 6, that helps you build it in your calculator if you need that help. But that means my x-intercept is -3, and I have a parabola that looks about like this. And then I have a line that's coming up through y equals x minus 1. Let's draw my parabola out a little farther. And then we're going to have a line that comes up through here about like this, y equals x minus 1. And this is y squared equals 2x minus 6. Let's go ahead and put it that way. Now I need to find my points of intersection. My double integral is the surface is xy, but these are the boundaries for the region that we're finding the volume under the curve, under the surface. So let's find our points of intersection. And I'm going to say that x equals, up here I'm going to say x equals y plus 1. And I'm going to put that into the other equation. And we get y squared equals 2 times y plus 1. And this should be plus 6. I copied that wrong. Plus 6. So then y squared equals 2y plus 2 plus 6. Y squared equals 2y plus 8. Y squared minus 2y minus 8 equals 0. Y minus 4, y plus 2, so y equals 4 and -2. So this point right here, the y value is -2, and if we plug that into the x, we get -1. So we have this point here, and then this point of intersection, the y value is 4, and 4 plus 1 is 5, so we have the point 5, 4. So these are our points of intersection. Now we're going to call this a type 2. You could call it a type 1, but then you have two different equations here. You have the red part of the parabola and the green part of the parabola if you put it in terms of x. Whereas if you put it in terms of y, you have one equation. So we're going to solve this for y, and we're going to say, we're going to solve this in terms of y. So we're going to solve for x. So we're going to say 2x equals y squared minus 6. So x equals 1/2 y squared minus 3. And up here we're going to say x equals, we're going to add 1 to the other side, so y plus 1. So now our equations are in terms of y. It is a type 2 equation. And when you have a type 2 equation, you're always going to read it towards the x-axis. So that is right to left. I have to stop to think about that every single time. So my lower boundary is going to be the parabola, and the upper boundary is going to be the y plus 1. Now remember, this double integral is xy. So let's come down here, and we're going to write our double integral with some spaces in it. Here we have xy. Now this is a type 2. So when we have a type 2, we're going to have a dx and then a dy. And our x boundaries are these equations. So here's the parabola is, remember we're reading it from right to left. So our parabola is our lower boundary. So we have 1/2 y squared plus minus 3. Minus 3, not plus 3. And then up at the top here, our upper boundary is going to be y plus 1. And then the easy way to remember that is that your last integral is going to be in terms of y, because you're going to have y's happening in these boundaries. So you have to wait to integrate with y once these y's get into the equation. And then because it's y, our lowest y boundary for the points of intersection are -2, and the upper one is 4. So we're going to say, so that is our integral. So you can memorize that it's type 2 and it's in terms of y. So your y comes last. It's just something to think about. So we're going to integrate from -2 to 4. Let's go ahead and integrate this with in terms of x. So when we integrate x, we get 1/2 x squared and we keep the y. And I'm going to say x equals 1/2 y squared minus 3 and x equals y plus 1. And then when we finish, we're going to integrate with respect to y. So now we have the integral from -2 to 4. We have 1/2. We should put a bracket here. We have y plus 1 squared times y minus 1/2 y squared minus 3 squared times y. And all of this, when we get finished, we're going to integrate with respect to y. Now, there is no nice, simple, easy way to do this, but at least it's not hard. It's just tedious. So I'm going to say 1/2 y and bring that y to the front. Y squared plus 2y plus 1. Remember, write it twice and do FOIL. Minus 1/2 y. We could have kept the 1/2 y out front. Maybe we'll do that anyway. 1/2 y squared becomes 1/4 y to the 4th. Minus 3 over 2. Minus 3 over 2 is -6 over 2, which is -3y squared, plus 9 with respect to, we're going to integrate with respect to y next. I'm going to pull this 1/2 y squared out, as I probably wish I'd done at the beginning, or the 1/2 y. So I have y squared plus 2y plus 1 minus 1/4 y to the 4th plus 3y squared minus 9. And then we're going to integrate with respect to y. So let's combine like terms. It keeps jumping when I move it. So we have 1/2 y. Let's go descending. So we have -1/4 y to the 4th. Does it really matter? Not a bit. Pick something and do it well. Y squared plus 3y squared makes 4y squared plus 2y minus 8 dy. Now you can't integrate that. You have to actually distribute the y, but let's pull the 1/2 all the way out front and not play with that crazy 1/2 if you're okay with that plan. So we have -1/4 y to the 5th plus 4y to the 3rd plus 2y squared minus 8y when we distribute that y. And now we can integrate this mess. So we get -1 over, this becomes the 6th. So we have 24y to the 6th plus, becomes y to the 4th. So it's just y to the 4th plus 2/3 y to the 3rd minus 8 over 2, which is 4y squared. And our bounds are -2 to 4. So now we need to evaluate. I'm going to keep my 1/2 out front, and I'm going to say 4 to the 6th over 24. Yeah. That becomes -512 over 3. 4 to the 6th is 4096 divided by 24. Both are divisible by 4. Both are actually divisible by 8. So that's what's going on there. And then we have 4 to the 4th, which is 256. And then we have 4 to the 3rd is 64 times 2 is 128 over 3. Minus 4y squared, 16 times 4 is 64. Then we're going to have to subtract all of those values at -2. So -2 to the 6th becomes a positive, but we got a negative. And it's 64 over 24, which is divisible by 8 to be 8 over 3. Plus 2 to the 4th is 16. Minus, because 2 to the 3rd is 8, so we have 16 over 3. And then it'll be a positive 4 times 4 makes it minus 16. So these 16s cancel beautifully. Life is pretty when that happens. So we have 1/2. I probably could use a calculator, but I'm in the mode and I'm doing it in my head, so we're going to keep going. I'm going to put the negative 512 plus 128 gives me negative 384. So I have negative 384 over 3. And 256 minus 64 gives me 192. And then I have negative 24 over 3, which becomes a positive 8. So I have 200 minus 384 over 3, which gives me a total of 72. And then half of 72 is 36. So the volume of this region comes out to be 36. Nice, pretty answer. Nice, pretty answer. This one says, find the volume of the solid that lies under the paraboloid stated here and above the region D in the xy plane bounded by y equals 2x and y equals x squared. So let's start with the fact that this is what we're integrating. So our double integral, I'm going to write it up here. Our double integral is x squared plus y squared with respect to a over d. Now, we have y equals 2x, which is a line that looks like this, and y equals x squared, which is a parabola that looks like this. So I would say this is a type 1 because you're in terms of x, or your equations, and it's nice and pretty, and it's working out that way. So your points of intersection, x squared equals 2x, x squared minus 2x equals 0, x times x minus 2 equals 0, so x equals 0 and 2. So my point of intersection right here is the point 0, 0, and this point is the point 2, 4. You kind of need to know all of that, and this is the area that the region is bounding, that z equals x squared plus y squared. Now remember it's a cone that goes up the z-axis because it's a circle that extends infinitely. So let's do our double integral over here. So we're going to say the double integral and x squared plus y squared. Now again, this is a type 1, so that means I'm going to put a dy and then a dx. The dx has to go last because my bounds go in terms of x. Now the upper bound is 2x and the lower bound is x squared. And then because we're in terms of x, our outside bounds are in terms of x, so they're going to go from 0 to 2. So now we're going to integrate first with respect to y. So we're going to keep the 0 to 2, and we're going to have x squared y plus 1/3 y to the third. And the bounds are x squared and 2x. And then when we get done, we're going to integrate with respect to x. I'm going to slide all this up and hope it stays. So we're going to keep this outside boundary. Now we have x squared times 2x, which gives us 2x to the third, plus 1/3 times the value of 2x to the third, which is 8x to the third. So we have 8/3 x to the third, minus x squared times x squared is x to the fourth, minus 1/3 x to the sixth dx. Now we have no like terms. We do have like terms. The first two are like terms, so let's combine those. So we have 2 plus 8/3 gives me 14/3 x to the third minus x to the fourth minus 1/3 x to the sixth with respect to x. Now we can integrate with respect to x. So we're going to get 14 over 3 times 1/4 x to the fourth minus 1/5 x to the fifth. My fifth is getting a little sloppy. Let me try it again. Minus 1/3 times 1/7 is 1 over 21 x to the seventh from 0 to 2. Now the good news is when we plug in 0, 0 to any power is 0, so all of that becomes 0. So let's say 14 over 12 reduces to 7 over 6. And we're going to do 2 to the fourth, which is 16, minus 32 over 5, minus 128 over 21, minus 0. And I'm just going to tell you that answer comes out to be 216 over 35. I'm going to let you pause and check that. I'm going to tell you that I'm confident it's correct and let you pause and check that. And this one says, find the volume of the tetrahedron bounded by the planes x plus 2y plus z equals 2, x equals 2y, x equals 0, and z equals 0. So because there's so much going on, it's best to start off with the three-dimensional figure. So let's start off with the three-dimensional figure, and here we have our XYZ plane. If we solve for x, we get x equals 2. If we solve for the y-intercept, we get y equals 1. Let me space these out a little bit more than I was doing just a minute ago, but you won't see those because I erased them. So x equals 2, y equals 1, and z equals 2. So let's turn this into the tetrahedron that we can see. So I'm kind of using a pencil tool here so you can kind of see the 3D figure. And if you were to turn it, it goes to the axis and it makes a triangular shape. And it's the surface that runs through all of that because it's that surface that sits on the front. So on the front we have this surface here. And then it's also bounded by x equals 0 and z equals 0. So you got to think about your xz plane. And so you've got your z equals 0 here, and then your x equals 0 down here. X equals 0 and z equals 0. In the background is the plane that hits it there. So let's pull it onto a 2D flat. So first of all, we want to think about what this means here. So we got a triangular tetrahedron hanging out. Oh, that was the first one. X plus 2y plus z equals 2. And then the second one is x equals 2y. So I don't know if I can put this on the same one. If you think about x equals 2y, it's a line that x equals 2y is the same thing as y equals 1/2 x. It's a line that looks about like this in 2D. So x equals 2y is a plane that runs through the z-axis, and it's a sheet of paper that runs out here. So it has a slope of 1/2, and it kind of extends. You can't see it, but if we were to draw it back, it's a plane that looks like this. So when it intersects this, you've got this plane coming through. So what we really have is this part of the tetrahedron here that goes all the way back, forming a triangle. I'm going to bring in the picture from the book, but I wanted you to see where they got it from. So this is what it looks like here. Now, we know that we already have this point. I covered up my pencil drawing over there. It's all good. So we have this point here of 0, 0, 1. We get this point right here because we're going to find the intersection. We're going to find it in just a minute. And we have the point up here for the z-intercept of 0, 0, 2. So we're in agreement with all of that. Now, at this point, what we need is this point right here that we haven't found yet. But let's go back to what we were given, and let's look at it. We have this equation here, x equals 2y, which we've already dealt with. X equals 0, fabulous, and z equals 0. Well, when z equals 0, that takes us into, we have x equals 2y. So if we take z equals 0 and put that into our other plane, we get x plus 2y plus 0 equals 2. Now, if we solve that and x equals 2y for the intersection, so let's say x equals 2y. Let's put that in. So we get 2y plus 2y equals 2. 4y equals 2. Therefore, y equals 1/2. And since x is 2y, then that means x equals 1. And that's how we get that point. When z equals 0, we get that point right there. So that gives us our 3 points. And we can now start to consider, but we have our tetrahedron. What we also need to think about is when we've done these graphs before, we've looked at the flat graph on a 2D surface, the XY plane, to figure out what we're doing. So I'm going to copy this equation down into the next a little bit farther down. Let's just bring it in. So we have x plus 2y plus z equals 2, and we have x equals 2y, and we have x equals 0, and we have z equals 0. So if we put this on a flat 2D surface, if we take let z equals 0, then this first equation becomes x plus 2y equals 2. Now let's solve that for y and say y equals negative 1/2 x plus 1. So we have a line that goes, that starts at 1, and it goes down 1 and over 2, so it's going to intersect somewhere over here. So we have a line. I know I missed it. Sorry. And then our other one, let's say y equals 1/2 x and solve for y. So that means we're going to start at the origin and come up and over. So we have a line that looks like this. So what we're really doing is this triangular region in here. Let's go ahead and say this is the region that's bounding our volume. So that's our flat 2D region we've been solving for, that is the boundaries for our volume. This top line here is y equals negative 1/2 x plus 1. And we have to decide if we're type 1 or type 2. And this bottom one is y equals 1/2 x. I would say we go with type 1 and do top minus bottom. So we're going to do the double integral, and we're finding the volume of this tetrahedron. Now we're going to go back up to this equation here and solve it for z. So z is equal to 2 minus x minus 2y. And we picked that one because that is our main tetrahedron happening here. The other equations that you were given are all part of our boundaries. So this one is part of the boundary, this one's part of the boundary, this one's part of the boundary. This is going to be our main curve. And it has a z in it. So it is a function in terms of x and y. Now since it's type 1, we're going to put dy and then dx. So our x equations, the bottom boundary is 1/2 x. The top boundary is negative 1/2 x plus 1. And then we need our point of intersection. We start over here, and this first boundary is x equals 0, and the second boundary right here is going to be x equals 1. I kind of missed it a little bit, but it's the point 1, 1/2. So our bounds go from 0 to 1. Now this isn't too hard of an integral once you get all that set up. That's the hard part. So we're going to go the boundaries from 0 to 1, and we're integrating with respect to y. So we're going to say 2y minus xy minus y squared, and the boundaries are y equals 1/2 x and y equals negative 1/2 x plus 1. Now the reason I wrote that in is because you don't see it, but I did it all by putting them in wrong. So maybe if I do it that way, I'll do them correctly this time. So we're going to say the integral from 0 to 1. So we have 2 times negative 1/2 x plus 1 minus x times negative 1/2 x plus 1 minus negative 1/2 x plus 1 quantity squared minus 2 times 1/2 x minus x times 1/2 x, or that's a plus 1/2 x quantity squared, and then we're going to integrate with respect to x. So let's distribute this mess. I'm going to throw a line in here and make a note that this is negative or positive 1/4 x squared minus 1/2 is minus 1x plus 1. All right, so I'm going to go ahead and distribute and say 2 times negative 1/2 x is negative x plus 2. Minus makes a plus 1/2 x squared minus x minus 1/4 x squared plus x minus 1. And then on the next line, this makes minus x plus 1/2 x squared plus 1/4 x squared with respect to x. Now we can cancel some stuff. So before we start this next line, I have a lot of these two cancel. The 1/4 x squareds cancel out. And these two cancel. So we can take those out. And then it looks like we're going to continue from there. Okay. So let's start with the x squareds. I have 1/2 and 1/2 makes x squared. And then I have a minus 2x. And 2 minus 1 is 1. Plus 1 with respect to x. That is a really pretty polynomial. It worked out very nicely. I'm super excited. I hope that you are. So when we integrate this, we get 1. We're integrating with respect to x. And since we're integrating, we shouldn't be writing the stuff at the front. So I just put a parentheses. And I have 1/3 x to the third minus x squared plus x from 0 to 1. So this means we have 1/3 minus 1 plus 1 minus 0, 0, 0. So the answer is 1/3. So that is the volume of the tetrahedron bounded by those planes. Fubini's theorem tells us that you could do your double integral in two different orders. Sometimes one is harder to evaluate than the other. And so that's a helpful idea to use when you're given a problem such as this one. The problem says the double integral. Let me fill in the correct things. So the first is from 0 to 1, and then from x to 1, and it says sine of y squared dy dx. Now, that is very difficult. It's impossible for you to integrate sine of y squared. We would have to estimate it, but it's not something that we can integrate. So what we need to do is change the order of integration. Now that's possible because we can say that f of xy is equal to sine y squared. And we can look at the region kind of like our rectangles, but let's call it D. D is our set of xy, the points, such that, now look at the fact that x is between 0 and 1, and y is between x and 1. So I read all of that off the integral and wrote it appropriately. Now, if we look at this region, let's go to this region and think about if x is between 0 and 1, let's not start there. Let's start with y is between 0. So this means y equals x, and this means y equals 1. So here's y equals x right here, and this is y equals 1 right here. So we're looking at this region in between the two, and it would help us if we could change it to make our integral go where we integrate with respect to x first and then with respect to y. Right now we're reading it as a type 1, and instead we need to read it as a type 2. So we need it to go this way. So what we want to do is we want to redefine it. We want to keep it f of xy equals sine y squared, but we want to change our region that we're working with. So we're going to start off with the fact that y goes from 0 to 1. Do you see that y goes from 0 to 1? That is definitely true based upon this picture. And now if you think about the x's, x has to be between two things. Now the x is between, this line right here is x equals 0, and this line right here is x equals y. So x is between 0 and y. So now we can build our double integral, leave some space in it, and we have sine of y squared. Now when we do this, we're going to put dx and then dy. So that means y is going to be in our first set of bounds. We're going to go from 0 to y, and the second set of bounds are going to be y from 0 to 1. Now that's a much easier problem to integrate at this point. You can actually integrate that because when you do, we're going to integrate first of all in terms of x. So pause and think about that and then go on. So we're going to integrate in terms of x. So we're going to say, when we integrate that, it doesn't have an x. We're going to say x sine y squared from x equals 0 to x equals y in terms of y. So we have 0 to 1, and x is going to be y sine y squared minus 0, so I'm going to leave that off, dy. Now this is not a bad problem to do at this point, because we can let u equal y squared, and then du is going to be 2y dy, so dy equals 1 over 2y du. Now when you do this, y is going to be 0, y is going to be 1. When y is 0, u is 0, and when y is 1, u is 1. So that works out nicely. 1 squared is 1. So we're going to rewrite this integral to be the integral from still 0 to 1, but now we're in terms of u. We did do change of bounds. Y of sine u times 1 over 2y du. Those y's cancel, because although we're in multivariable calculus, you still integrate in terms of one variable. I'm going to pull the 1/2 out front. And now the integration of sine of u is negative cosine of u from 0 to 1. So we have negative 1/2 cosine of u plus 1/2 cosine of 0. This u is 1. Let's go back and make this a 1. So negative 1/2 cosine of 1, which we don't know, so we're going to leave it that because it's exact, plus cosine of 0 is 1, so we get 1/2. We could rewrite it to be 1/2 minus 1/2 cosine of 1. We like it that way. Or you could factor the 1/2 out and say 1 minus cosine of 1. But the goal here is to understand that if we can change the order of the integration, and it works out very nicely for us. The directions on this problem say sketch the region of integration and change the order of the integration. Notice that you don't even have to integrate, you just have to change the order. So you're going to say f of x, y, and you're going to break it down. So let's say that the region is, first of all, x is your outer boundary, so x is between 0 and 4. And then y is between x squared and 16. So now you're going to draw your xy plane. And x squared is a parabola that looks like this. And 16 is your upper boundary. So this is the region that we have here, and it's bounded by this parabola. But x is between 0 and 4. So let's undo that shading. X is between 0 and 4, so it's this right here. And let's label them accordingly. This is y equals 16, and this is y equals x squared. So here's the real big deal. We want to change types. Right now we are going from 16 to x squared, the upper to lower boundary. And we want to change types. This is currently a type 1, and we want to change it to a type 2. I am not going to ask you what type it is. I just need you to be able to figure out how to do that. So we're going to go this way, and we're going to say the double integral of f of xy. And we're going to say we're switching the dx and the dy. Now, it may be easier to go ahead and change it up here and say xy such that now my y boundary is going to go from 0 to 16. So we're going to say y is between 0 and 16. Now we need to talk about x. This one is x is equal to the square root of y. So we take the square root of both sides. X is equal to the square root of y. That's this equation right here. And then the other one is x is equal to 0. So we're going to have x is between 0 and the square root of y. So that helps you build it. So then x is between 0 and the square root of y, and your y boundaries are 0 to 16. Change of bounds isn't real hard as long as you stop and think about what this graph is, and 2 different colors really does help. I highly recommend it. So this graph right here in blue is the one they're looking for. Blue and pink, because really they just are looking for the equations and the shading. And then they are looking for you to rewrite it, your region, and to come up with the double integrals with the bounds. And I hope that you enjoy this lesson. Make sure that you're practicing the concepts. I really didn't give you a ton of them. Just set similar question and do them a couple more times if you need to practice more. Have a great day, and I hope you enjoy this lesson.